Good morning students. Today we are going to discuss the next topic of our chapter, that is kinetic theory of an ideal gas. So all matters are made up of molecules, okay? And the molecules of gas are in state of rapid and continuous motion. Okay, all the molecules are in the rapid and continuous motion. They are in motion. Their velocity depends on temperature. Using this molecular motion, various properties of gas like pressure, temperature, energy, etc. can be explained. Hence, the theory is called kinetic theory of gases because on the basis of the molecular motion we can explain these different properties of the gas. Okay, so this theory was developed by Clausius and Maxwell. Now there are many assumptions in this theory. First is all gases consist of molecules. We know that the molecules are rigid elastic spheres. That means their shape is a sphere and they are elastic spheres, identical in all respects for a given gas. For a particular gas, all the spheres are identical and different for different gases. If we are talking about the different gases, then the molecules are different. The size of a molecule is negligible compared with the average distance between the molecules. We know that the molecules of gases are having large distance between them. Okay, so the size of molecules is very less as compared to the distance between these molecules. Third point, the molecules are in a state of continuous random motion. We know that moving in all directions with all possible velocities. Fourth point, during the random motion, the molecules collide with one another and also with the walls of a vessel. If molecules are filled in a vessel, then they will collide with each other also and they will collide with the walls of the vessel also. So during collision, their velocities are changed in magnitude and direction also. The magnitude of the velocity will also change and the direction of the molecules will also change. Fifth point, the collisions are perfectly elastic and there are no forces of attraction or repulsion between the molecules. Okay, the collisions are perfectly elastic. That means the momentum before collision and the momentum after collision will be same. Okay, so and there are no forces of attraction or repulsion between the molecules. Thus all internal energy of gas is kinetic, because if there are internal forces of attraction or repulsion, then potential energy will be there. But we know that for ideal gas there is no motion, no attraction or repulsion forces between the molecules, so the internal energy will be purely kinetic. Then between two collisions, a molecule moves in a straight line path with uniform velocity v. Okay, and the average distance covered by a molecule between two successive collision is called the mean free path. That means for how much distance it will remain in the free state, that is the mean free path. We will calculate the average of the two successive collision. Okay, that is the mean free path. The collisions are, that means average distance between the two collision. For example, here the collision is going on and after striking this molecule will collide with this. So this is the distance for which it will remain in free state, and we will calculate all the averages. We know that we have done this in the class also. So that is called mean free path. The collisions, the seventh point, the collisions are almost instantaneous. That means the time during which collision lasts is negligible compared to the time of free path between molecules. For how much time they are colliding, that is negligible. Last point, in spite of molecular collisions, the density remains uniform throughout the gas. Still there are collisions of the molecules, still the density of the molecules will remain, density of the gas will remain same. Now next is the derivation for calculating the pressure of an ideal gas. For this, consider a gas enclosed in a cube of side L. This is a cube of side L. We are considering a gas enclosed in it. So take the axis to be parallel to the sides of the cube as shown in the figure. A molecule with velocity Vx, Vy, Vz hits the planar wall parallel to YZ plane. This is x axis, this is y axis, and this is z axis. Okay, so we have, this is the YZ plane. We have taken a plane parallel to the YZ plane. This plane we are taking. Okay, and the velocities in x direction, y direction, and z direction are these Vx, Vy, and Vz, and the plane area will be A, that is equals to L square. Okay, since the collision is elastic, we know that the collision is elastic according to the kinetic theory of gas. So the molecules rebounds with the same velocity. So its y and z component of velocity do not change in the collision, but the x component reverses sign. That is, the velocity after collision will be negative of x, and velocity in y and z direction will not be changed. This is the molecule in initial phase. After some time it collides with the wall of area A. Okay, so now the collision is elastic, so the velocity in y and z direction will not change, but the velocity in x direction will be reversed. The velocity will remain same na. The change in momentum of the molecule. Now what will be the change in the momentum of the molecule? See, velocities in y and z direction have not changed even in the magnitude and even in the direction, but velocity in x axis changed in direction. Its direction got reversed, so the momentum will be changed in this direction. So the change in momentum of the molecule will be final momentum, this is the negative mvx, this is the final momentum minus initial momentum, that is mvx, so it will be minus of 2mvx. Okay, and by the principle of conservation of momentum, the momentum imparted to the wall in the collision is 2mvx, because this is the momentum, change in the momentum of the gas molecule. For one gas molecule we are discussing this. Okay, so this is the change in momentum for the gas molecule, so that means this much momentum will be transferred to the wall. Correct? Now I have derived this in simpler language. For derivation you can take this. Now change in momentum molecules is minus of 2 mvx, and by conservation of momentum, the momentum imparted to the wall in the collision will be positive of 2 mvx. Correct? So in small time interval, let we are talking about small time interval delta t, all those molecules which lies within the distance vx delta t. See, this was wall. Okay, and it was striking, it was going with vx velocity in delta t times. So in delta t times, distance covered by this will be vx into delta t. Correct? So which lie within the distance vx delta t from wall of area A, the area of the wall was A, will hit this wall. Correct? The molecules in delta t time interval, the molecules which are at distance vx delta t from the wall will only collide the wall. So that is, actually we want to calculate the number of molecules. Okay,
Since
okay, so the those molecules which lie within this distance from the wall of area A will only hit the wall. That is, the molecules which lie in volume A into vx delta t. This vx delta t is the distance near the wall of area A. So the volume near the wall will be A into L. So here it will be A into vx delta t. This much volume is near the wall. Okay, and the molecules present in this volume will only hit the wall in time delta t. So on the average, half of such molecules are moving towards the wall and other half away from the wall. Okay, that means if this is the volume in which this is the distance Vx delta t and molecules are here, some molecules are there in this wall. Okay, so at a particular time, if we will consider this case, at a particular time some molecules were going towards the wall and some were going away from the wall now, because at what time we are observing them, at that time some molecules have already collided with the wall, correct. So that means some molecules were going away from the wall after the collision and some molecules were going towards the wall for the collision. Okay, that means on an average half of the molecules, on an average half of the molecules are moving towards the wall and other half were moving away from the wall. So now we want to calculate the number of molecules hitting the wall. How much molecules will hit the wall? So let us consider number of molecules per unit volume is small n. Small n is the number of molecules per unit volume. Okay. So the total volume is this. That means the total number of molecules present in the V volume will be n into V. And here what is the value of V? It is A into Vx delta T. These are the total number of molecules present in this volume, and we know that how much molecules will collide? Only half of this molecules will collide. So half of n Vx delta T. These are the molecules will collide the wall, and this amount of molecules will also be going away from the wall. Now the total momentum transfer to the wall will be equals to what? This was the momentum transferred to the wall by one molecule, and these are the total number of molecules. So the total momentum transferred will be 2mvx multiplied by half of avx delta t n. This is the total momentum transferred to the wall. Now the force on the wall will be delta p by delta t. Here delta p is the change in momentum. How we are getting delta p by delta t is equals to force? Because momentum is equals to mass into velocity, correct. So this is our momentum. Now if we will divide it by time, that means p by t, so v by t is equals to what? It is equals to acceleration. That means it is mass into acceleration, and which is equals to force. That means momentum upon time is force. So that means force on the wall will be change in momentum upon small time interval which we are considering. So the force will be equals to nm vx square a. Now we want to calculate the pressure on the wall. So pressure is equals to force upon area. So this quantity is divided by a. So a to a will be cancelled out. The quantity remaining will be nm vx square. This is the pressure exerted by the molecules on the wall. Now as molecules move with different velocities, so we replace vx square by its average velocity, that is vx square bar. Okay, because it is not confirmed that all the molecules will be moving with vx velocity. Okay, so we have taken the average velocity in x direction, that is vx bar, and taken square of that, so it become vx bar square in this equation. So this equation will become pressure is equals to nm vx bar square. Now gas is isotropic. That means in all the directions the velocities are same, almost same. So the v bar x square will be equals to the v bar y square will be equals to the v bar z square. So average of all these will be equals to vx square plus vy square plus vz square by 3, that is 1 by 3 of v bar square. This is the average of all these. Okay, because the particles were not moving only in the x direction now, we have to consider all the velocities in all the directions. So we will take average of all those, and that will be equals to 1 by 3 v square. So now we will replace Vx bar square to 1 by 3 V bar square. This is the average of all. So the total pressure exerted on the wall will be equals to 1 by 3 Nm V bar square. This is the pressure exerted on the wall. Now kinetic interpretation of temperature, the new topic. We know that pressure exerted on the ball will be equals to this 1 by 3 Nm V bar square. Now multiplying both sides by capital V. Capital V is the volume. So PV is equals to 1 by 3 small n V small m V bar square. Now small n into V is equals to total number of molecules, that is capital N. Total number of molecules present in the V volume, or we can say V volume of sample. Sample means sample of gas. So now PV is equals to 1 by 3 capital N small m V bar square. Okay. Now if we multiply this equation by 2 and divide this equation by 2, we can do this now, because 2 to 2 will be cancelled out and only this value will be remaining. That means the value of this quantity is not going to change if we multiply it by 2 or divide it by 2. Okay. We are doing this so that we can make it like half of mv square, that is kinetic energy now. That's why we are doing this. So now this equation will become this: PV is equals to 2 by 3 N into half of mv bar square. Here half of mv bar square is average kinetic energy of molecules of gas, because we have taken v bar as the average velocity now. So this is the average kinetic energy of molecules of gas. And for ideal gas we know that internal energy is purely kinetic now. For ideal gas the internal energy is purely kinetic. That means this kinetic energy will be equals to the internal energy of the gas, and that is we are denoting here it by E. So this is the internal energy of the gas. So the internal energy will be equals to capital N, these are the total number of molecules, multiplied by the average kinetic energy of one molecule, that is half mv bar square. Okay. And E by N is equals to half mv bar square. That means the internal energy per molecule. This is the internal energy per molecule. Now put this value in equation 1. This was our equation 1. PV is equals to this. So N into half mv square will be equals to what? E. We will put this value in the equation. So PV will be equals to 2 by 3 E. Now this is our equation 2. Now for ideal gas we know that PV is equals to mu RT, and previously we have derived also that R is equals to KB Na, where KB was the Boltzmann's constant and Na was the Avogadro's constant. So R was equals to KB Na, we have derived it previous expressions. So it will become mu KB NaT. Now we have arranged so that mu and Na comes closure. So it will become PV is equals to mu Na into KBT. Now we know that mu is equals to N upon Na, where N is the total number of molecules and Na is the number of molecules in Avogadro's constant, that is 6.022 into 10 raised to power 23. That means capital N will be equals to mu Na. So here we will put the value of mu Na as capital N. Then this equation will become PV is equals to KBNT. Now we will equate equation 2 and equation 3. So we will get 2 by 3 of E will be equals to KBNT. That means E will be equals to 3 by 2 KBNT. And this E is the internal energy of the gas. So for one molecule, this is the total internal energy now. So for one molecule, this energy will be equals to E by N, and that is equals to 3 by 2 kBT. So the average we can say now, this is the average kinetic energy also now, because the average kinetic energy was equal to the internal energy. This is the average kinetic energy we have derived. That means from this expression we can say that here Kb is constant, 3 by 2 is fixed value. That means the average kinetic energy of one molecule is proportional to the temperature of that molecule. That means half of mv bar square is proportional to T, because E by N was half mv square now. We have derived this. So it is independent of pressure volume and nature of ideal gas. This is the fundamental result that relates temperature of a gas to the average kinetic energy of the molecule. Okay. That means the kinetic energy of the molecule depends only on the temperature of the gas. Now root mean square speed. The square root of mean square speed, that is v bar square, this is v bar square, is known as the root mean square speed. Okay, because this is the mean square speed na, mean speed square, so this is mean square speed, and if we will take root of this, so this will become root mean square speed, and it is denoted by VRMS, root mean square. From kinetic interpretation, we know that half of m v bar square is equals to 3 by 2 kBt. We have derived this. So v bar square will be equals to 3 kBt by m. 2 to 2 will be cancelled out, and this m will go in denominator. This will become 3 kBt by m. This is what? Mean square speed. We want to calculate the root mean square speed. So taking square root both sides, this will be root mean square speed, and this is root over 3 kBt by m. So this is our root mean square speed, that is denoted by VRMS. So it is equals to 3 root over 3 kBt by small m. Now if directly mass of the gas is not given, then we can calculate by formula. We know that mu is the number of moles is equals to mass of the gas divided by the molecular mass, and also total number of molecules divided by the Avogadro constant. So that means small m will be equals to capital M molecular mass multiplied by the number of molecules divided by the Avogadro constant. Now for one molecule n is equals to 1, so small m mass of the gas will be capital M upon Na. So if directly the mass of gas is not given, then we can calculate it by molecular mass divided by the Avogadro constant. Now there is numerical regarding this. A flask contains argon and chlorine in the ratio of 2:1 by mass. The temperature of the mixture is 27 degrees Celsius. Obtain the ratio of first average kinetic energy per molecule and root mean square speed VRMS of the molecules of the two gases. The atomic mass of argon is given 39.9 unified mass U, and molecular mass of chlorine is 70.9 U. Okay, that means this capital M is given for both argon and chlorine. So the important point to remember is that the average kinetic energy per molecule of ideal gas is always equal to the 3 by 2 kBt. That means it depends only on the temperature, and here the temperature is same for both the gases. That means since argon and chlorine both have the same temperature in the flask, so the ratio of the average kinetic energy of the two gases will be 1:1, because their kinetic energies will be same, and we want to calculate here ratio only, average kinetic energy per unit molecule, ratio of, obtain the ratio of these, and also the ratio of the root mean square speed. For that also we have to calculate ratio. So this is 1:1. Now we know that half of mv RMS square is equals to 3 by 2 kBt. Okay, so VRMS square will be equals to small m chlorine, because here VRMS is inversely proportional to the root of m, and VRMS square will be inversely proportional to the root over m, because this was square root of m na. So VRMS square will be proportional to 1 upon m. So if we are talking about the VRMS square of argon, so it is 1 upon argon na. That means if we will take the ratio of the VRMS square of argon upon VRMS square of chlorine, then that will be equals to mass of the chlorine upon mass of the argon, because the ratio is inverse na, the relation is inverse. Now we know that how to calculate the mass. Mass is equals to capital M upon Na, that is molecular mass upon Avogadro constant. Again, Avogadro constant is Avogadro constant is a constant value. So if we will take the mass of chlorine upon mass of argon, Na to Na will be cancelled out now. So only the remaining value will be molecular mass of chlorine and molecular mass of argon. Correct? Only these will be the remaining value. So here the mass of chlorine upon mass of argon will be equals to molecular mass of chlorine upon molecular mass of argon, and that is given 70.9 upon 39.9, that is equals to 1.77. Now we have calculated the ratio of the VRMS square. We want to calculate the ratio of the VRMS speed. Okay, so the ratio of the VRMS square will be root over this value, root over 1.77, and that is equals to 1.33 answer. Okay, now the next topic is Maxwell's distribution function. In a given mass of gas, the velocities of all molecules are not same. We know that. Even when bulk parameters like pressure, volume and temperature are fixed, then also the velocities of all the molecules are not same. That's why we have taken the average velocities of all those. Collisions changes the direction and the speed of the molecules. However, in a state of equilibrium, the distribution of speeds is constant or fixed. Okay, if we are considering the equilibrium state, then the distribution of speeds, that means how much speed we are distributing, we will distribute in different columns, in different ranges. So that distribution will be same or fixed. So distributions are very important and useful when dealing with systems containing large number of objects. We know that distribution is important. For example, consider the ages of different persons in a city. It is not feasible to deal with the age of each individual. We can divide the people into groups: children up to 20 years, adults between age 20 to 60 years, old people above 60 years. If we want more detailed information, we can choose smaller intervals: 0 to 1, 1 to 8, 1 to 2 and 99 to 100, so on. So this can be distribution on the basis of different ages or on the basis of different age groups. So when the size of the interval becomes smaller, this is the size of the interval, the size of the interval becomes smaller, say half year, the number of persons in the interval will also reduce. Correct? If we will reduce the size of the interval, for example, if we are taking half year, that means 0 to 0.5 is one group, then 0.5 to 1 is another group. Okay, then what will happen? The number of people will also halved. Correct? So roughly half the original number in 1 year interval. So the number of persons, that is D and X, D is for small, in the age interval X and X plus dx is proportional to dx or D and X, that is equals to nx into dx. Number of person, this is number of person dnx in the age interval x to x plus dx, that is proportional to what? That is proportional to dx. That means this was the interval between them na. So the number of person is proportional to the interval also. Correct? The more the interval, the more will be the number of person in that interval. So if this is dnx, the number of persons in x interval, that will be proportional to dx, the time interval between the two ages. Okay, so that means d and x will be equals to, if we will remove the proportionality sign, that will be equals to nx dx. Nx is the constant. We have used nx to denote the number of persons at the value of x. Here nx is the number of persons at the value x. Okay, and this is the Maxwell's distribution of molecular speed. In a smaller way, the molecule speed distribution gives the number of molecules between the speeds v and v plus dv. The same formula is applied for the molecular distribution, and he have derived the expression this expression he have derived for the molecular distribution. D and V, these are the number of molecules at V speed, and that is equals to 4p n a cube e to the power minus bc square v square dv. That is equals to nv dv. Here nv is that constant. Okay, this is called the Maxwell's distribution. The plot of nv, this nv is the constant. The plot of nv against v is shown in the figure, and the fraction of the molecules with speed v and v plus dv is equal to the area of the strip shown. We can calculate how much molecules present in delta v interval. This delta v is the speed. Okay, this is the interval of the speeds, because here the variation is the speed. They have different speeds now. So the average of any quantity like v square is defined by the integral of this. If you want to calculate the v square, this is calculated by integration of this. Okay, this was the root over 3 kbt by m. This is equals to over v rms square now, which agrees with the result derived from the more elementary consideration. This is not actually in our course. We have only this curve. Okay, this is the Maxwell's distribution function. Now there is another example. Uranium has two isotopes of masses 235 and 238 units. Okay, these are the two isotopes of uranium. If both are present in uranium hexafluoride gas, which would have the larger average speed? We have to calculate out of these two which will have the larger speed. If atomic mass of fluorine is 19 units, atomic mass of fluorine is given and both the masses are also given. Estimate the percentage difference in the speed or at any temperature. Temperature is not mentioned, we can take any temperature, and we have to calculate the percentage difference in the speed. That means the temperature for both is same. Now at a fixed temperature, the energy is equals to half mv bar square, correct? And that value will be equals to constant for both, because they depend only on the temperature. So smaller the mass of the molecule, faster will be the speed. See, this value is constant now, because temperature is constant. That means m into v square is constant. That means v square is inversely proportional to mass now. That means if mass will decrease, velocity will increase, correct? So smaller the mass of the molecule, faster will be the speed, correct? So the ratio of speeds is inversely proportional to the square root of the ratio of masses. We can clearly see this, because v square is inversely proportional to m. That means v is inversely proportional to root m. That means v1 upon v2 will be equals to root over m2 upon m1, correct? So we are taking, okay, see, so the square root of the ratio of the masses are 349 and 352 units. How we got these masses? We were given uranium hexafluoride. Okay, so if we are talking about the 235 mass of uranium, then the mass of the uranium hexafluoride will be equals to what? Mass of uranium plus hexafluoride 6 into F now. So 235 plus 6 into atomic mass of fluorine is given, that is 19. So this will be equals to 235 plus, what will be this value? This is equals to 114. So this will be equals to 349. Okay, so for the 235 molecule it will be 349, and for the other one 238 units mass it will be 352. So now we are taking the ratio of the velocity of 349 upon 352, that will be equals to root over 352 upon 349, and if we will calculate this value, this will be equals to 1.0044. Okay, so and we want to calculate the percentage change in the velocity, that will be delta v upon v, that will be equals to 0.44 percentage. Okay. Here U-235 is the isotope needed for nuclear fission. So to separate it from the more abundant isotope U-238, the mixture is surrounded by a porous cylinder. Actually what happened now, these two molecules stay together, okay, and this U-238 is present in more abundant, okay. So we have to separate this U-235 isotope from this U-238 for the nuclear fission. That means to react with the nucleus, and if we want to create the nuclear blast, we want to create the nuclear energy, then this uranium is required in that case. Okay. So we have to separate this from U-238 isotope. So for that, what we have to do, the mixture is surrounded by a porous cylinder. The porous cylinder must be thick and narrow, okay, so that the molecules wanders through individually, colliding with the walls of the long pore, and the faster molecule will leak out more than the slower one. Okay, this is our cylinder, and here the gas will present, the molecules of the gas will present. We know that the U-235 having less mass, that means its velocity will be faster than the 238. Okay, so what will happen, we will create the narrow path in the cylinder, okay, and this cylinder is a porous, okay. So the porous cylinder must be thick and narrow so that the molecules wanders through individually, colliding with the walls of the long pore. The molecules will collide with the pores, so the faster molecule will leak out more than the slower one, and so there is more of the lighter molecules enrichment outside the porous cylinder. The molecules which are faster will be more in this side now, because they will strike with the walls. If the speed is more, then they will strike faster, and they will reach here in more numbers. So the molecules will reach in this side will be more, that will be of smaller mass or greater velocity, and that is U-235, which we require for the nuclear fission. Okay, so by this process we can separate the uranium-235 from uranium-238. So the method is not very efficient and has to be repeated several times for sufficient enrichment, because some of the U-238 molecules will also mix with them now. So we have to repeat this process again and again. Okay. Now the next topic is degree of freedom. The degree of freedom of a dynamical system are defined as the total number of coordinates or independent quantities required to describe completely the position and configuration of a system. What is degree of freedom? It is the degree of freedom of a dynamical system. For a system, the degree of freedom is defined as the total number of coordinates or independent quantities required to describe completely the position and configuration of a system. That means these are actually the total number of coordinates, okay, or the total number of variables we have to describe, we have to give to describe the complete position and configuration of a system. That means the system is in translation motion, in a rotational motion, or whatever, or in how much directions the motion is there, we have to define that. That is the degree of freedom. That means in how many ways the molecules of the system can move. Okay, that is the degree of freedom now. That means how much freedom is given to the molecule, in which directions it can move, and by how many ways it can move. That is actually the degree of freedom, and that is calculated by the total number of coordinates required to describe the position and configuration of the system. That is actually the degree of freedom. That means how much freedom is given to a molecule for its motion in normal language. Okay, So it is actually represented by small f, and this is given by small f is equals to 3n minus k, where capital N is the number of particles in a system and k is the number of independent relation between the particles. What is this? We will know it further. For now, just remember the formula. F is equals to 3n minus k, where n is the number of molecules in a system and k is the number of relation between those particles. Now first, the degree of freedom of a monoatomic gas. Monoatomic gas means the gas which is having only one atom, that is monoatomic gas. So the molecule of a monoatomic gas, like helium is a monoatomic gas, neon, argon, these are the monoatomic gas now. So the molecules of a monoatomic gas consist of a single atom, that is a point mass. They have only a single atom na. So it is capable of translatory motion only. So this molecule can do only the translation motion. So it has 3 degree of freedom. See, this is the molecule of helium gas. Now we have 3 axes. This is x-axis, this is y-axis, and this is z-axis. This molecule can do translation motion in x-axis, can also do the translation motion in y-axis, and can also do the translation motion in z-axis. Okay. Now if this molecule is here, also it will have only the 3 coordinates na, x, y and z only. So only 3 coordinates are required for this to show the motion of this, in which direction it is doing the motion, okay, or it is in moving. So these 3 are the degree of freedom of the monoatomic gas. Okay, so here the number of particles is 1 in a system, and how many relations are there? There is no relation or no restriction. So k is equals to 0. Now put these values in the formula. F is equals to 3n minus k. So it will be 3 into 1 minus 0, that is equals to 3 also. From this formula also we are getting 3 degrees of freedom. So these are the degree of freedom for a monoatomic gas which is having only one molecule. Now the degree of freedom of a diatomic gas which are having 2 molecules like N2, O2, H2, CO. That means 2 atoms in a one molecule, not 2 molecules. So the molecule of a diatomic gas like N2, O2, H2, CO, etc. consists of 2 atoms A and B. For example, these are the 2 molecules A and B. This is N and this is also N, then this is N2. This is N2 na. At a fixed distance apart. The distance between these 2 molecules is fixed. Okay. Now, corresponding to the translatory motion, the molecules has 3 degree of freedom. Okay. These 2 molecules can also do the translatory motion in x-axis, y-axis and z-axis. So according to the translatory motion, it have 3 degree of freedom. Okay. So from the translatory motion point of view, it will have 3 degree of freedom. Okay. But the molecule has 2 additional degree of freedom due to the rotational motion about 2 mutually perpendicular axes passing through its center of mass. As the atoms are point masses, so the rotation is not possible about line AB. See, now this system can rotate about y-axis. Okay, this complete system can rotate about y-axis in this manner. Okay, and this can also rotate about z-axis. This is our z-axis. This can also rotate about z-axis also. Okay, but this can't be rotate. This is the molecule of okay, and this is also the x-axis. So this can't rotate about this axis in this manner. So the rotation in x-axis is not possible, but the rotation will be there in y-axis and z-axis. Okay, so there are 2 more degree of freedom for the diatomic molecule. So the rotation is not possible about line AB, that is in x-axis. So the rotary motion contributes 2 more degrees of freedom. So the total degree of freedom is 5. And now from the formula point of view, There are two atoms, so n is equals to 2. Okay, and there is one independent relation between the particles of the system. This is the relation, this is the restriction na. This is the restriction between the two particles. So the number of restriction is 1, or we can say the number of relation is 1. So k is equals to 1 and n is equals to 2. Put these values in the formula, then degree of freedom will be 5. Now at higher temperature, for example at approximately 5000 Kelvin, a diatomic molecule has 2 additional degrees of freedom due to the vibrational motion. Okay, at higher temperature the diatomic molecule starts vibrating. So each vibrational has both kinetic and potential energy. Okay, each vibrational motion has both the kinetic and potential energy. So 1 degree of freedom of vibrational motion is taken as 2. Okay, that means it will have one degree of freedom for the kinetic motion, for 1 degree of freedom for the vibrational motion, and that 1 degree of freedom will be considered as 2 because it will have the kinetic energy also and the potential energy also for the vibration point of view. So it will have 2 more degrees of freedom. That means the total of 7 degrees of freedom at this much temperature. It will have 7 degree of freedom due to the vibrational motion. Okay, now third one, the degree of freedom, d of s degree of freedom of triatomic molecule. Now these are also two types. First, the non-linear molecules. If the molecules are non-linear, so like S2O, SO2, here 3 atoms located as 3 vertices of a triangle in this manner. This is the non-linear case. That means molecules are not arranged in the linear form. Here F is equals to 3. Correct. Sorry, N is equals to 3. This is not F. N is equals to 3 and K is also equals to 3. The relation between the molecules is 3 na. The restriction, the 1, 2, 3. This is the relation between the molecules. So K is also equals to 3. N equals to 3 and K equals to 3. Put this value in the degree of freedom formula. F is equals to 3 into 3 minus 3. So F will be equals to 6. That means it will have 6 degrees of freedom. Now if we will talking about the linear molecule like CO2, it has 3 atoms arranged along a straight line. So this is the linear molecule. In this, number of molecules is 3, but the relation between the molecules is only 2. This 1 and 2. So here the degree of freedom will be 7. N is equals to 3, K is equals to 2, so it will become 3 into 3 minus 2, that is equals to 7. Okay, so this was degree of freedom. Now the next topic is law of equipartition of energy. It states that in any dynamical system, in thermal equilibrium, the energy is equally distributed among its various degrees of freedom. That means how much degree of freedom will be there in any system, the energy will be equally distributed among them. And energy distributed with each degree of freedom per molecule, the value of energy which will be distributed between those molecules will be half kBT. This is the law of equipartition of energy. Okay, that means for each particular type of motion, for each degree of freedom, this much energy will be there for a molecule, where Kb is the Boltzmann's constant and T is the absolute temperature of a system. So consider one molecule of a monoatomic gas in thermal equilibrium at temperature T. Okay, so a monoatomic gas molecule can be taken as a point mass. So each such molecule has 3 degree of freedom. We know that for a monoatomic gas the degree of freedom is 3 due to the translatory motion only. We know that for monoatomic gas only there is a translatory motion. So according to the kinetic theory of a gas, the average translation kinetic energy of a gas molecule is given by, we have derived this expression now in the kinetic interpretation, that is according to the kinetic theory of gas, that is half of mv bar square will be equals to 3 by 2 kBT. We have derived this, where v bar square is the mean square velocity of a gas molecule, of mass m. Now if vx bar square, vy bar square, vy bar square, vz bar square are the components of the mean square velocity, which we know that in different direction these were the components of the velocity of v bar square of a gas molecule along the three coordinates axis, then v bar square is equals to sum of all these. Okay, so half of vm x square plus half of vm y square plus half of mvz squares will be equals to 3 by 2 kbt. Correct. Actually the velocity is equally distributed in all the direction now. So if so, this velocity square will be equals to sum of all these three. Okay, so this was the value now, half of mv bar square. Okay, so if we will put the value of v bar square is equals to vx square plus vy square plus vz square, then this equation will become in this form. Half of m will multiplied by all these three. So this will be the value. Now as molecular motion is random, there is no preferred direction of motion. Okay, the direction of motion is not preferred because molecular motion is random. The molecules are moving in the random direction. So the average kinetic energy of each molecule along each of three axes is same. In all the three axes the velocity will be same. That means these all three will be equal. Now combining the above two equations, we will get that what we will get, the sum of all these three will be equals to 3 by 2 kbt na, and all these are equal, then we will get half of half of mvx square will be equals to half of mvy square and will be equals to half of mv square, that will be equals to half of kbt. How? Because all these three are equal, that means if we will take this also vx square, this also vx square, then this complete value will be equals to 3 by 2 m vx square na. Correct. So 3 to 3 will be cancelled out, that means half of mvx square will be equals to half of kbt. Correct. 3 to 3 will be cancelled out, so this value will be equals to half of mvx square will be equals to half of kbt, and that half of mvx square is also equals to half of mvy square, half of mvz square. So that means all these three are equals to half of kbt. That means half of kbt energy is given to each degree of freedom. These are the 3 degree of freedom in 3 direction na, in x axis, in y axis and in z axis. These are the degree of freedom for the translatory motion. Correct. So the average kinetic energy per molecule per degree of freedom is half kbt. This result was first deduced by Boltzmann and it is called the law of equipartition of energy. Now the law holds good for all degree of freedom, whether it is a translation, whether it is a rotational or whether it is a vibrational. For all degree of freedom this law holds good. That means this law is valid. A monoatomic gas molecule has only only translational kinetic energy na, so it is denoted by ET, translation kinetic energy, and that is equals to half of mvx square plus half of mvy square plus half of mvz square. So monoatomic gas molecules have only 3 degree of freedom. Now in addition to translation kinetic energy, a diatomic molecule has 2 rotational degree of freedom also. That means it will have 2 rotational kinetic energies also. So the total energy will be ET plus ER, that is the energy in translation, and this is the energy of rotation. So the 3 translation degree of freedom will be this, half mvx square, mvy square and mvz square, and the 2 rotational degree of freedom will be this. For rotation the kinetic energy will be given by this. The mass will be replaced by I, that is the moment of inertia, and the velocity will be replaced by omega, that is angular momentum or angular velocity, sorry, not angular momentum. This I is moment of inertia and this omega is the angular velocity. in place of velocity for rotation it will be angular velocity, and in place of mass it will be moment of inertia. This was actually the part of the 7th chapter. Okay, the rotational motion. So now the particle is not rotating about x-axis now, because the particle was itself in x-axis, so it is not able to rotate about x-axis. That's why the rotational motion will be in y and z direction. So omega y and omega z are considered here. Okay, here the line joining the two atoms has been taken as x-axis, about which there is no rotation. So the degree of freedom of a diatomic molecule is 5. It doesn't vibrate. Okay, if it is not vibrating, that degree of freedom is 5. Now diatomic molecules like CO, carbon monoxide, has a mode of vibration even at moderate temperatures. So its atoms also vibrate along the interatomic axis and contribute a vibrational energy term EV. This is the vibration energy to the total energy. So the total energy will become this ET plus ER plus EV. And here the vibrational energy is given by this. We will discuss in the vibrational motion chapter. Half of m dy by dt whole square and half of ky square, where k is the force constant of the oscillator and y is the vibrational coordinate in which direction vibration is going on. Okay, so this is the law of equipartition. After this we will discuss in the class. Okay, only 2 to 3 topics are remaining after this. Okay, thank you.